So good morning, everyone. Thank you for attending the webinar. Welcome. This is Q-Chem's 65th webinar. Thomas Jagau is going to be covering his work with non-Hermitian quantum chemistry methods in Q-Chem. Professor Jagau is an associate professor of theoretical chemistry at KU Leuven. He obtained his PhD in 2013 from the University of Mainz, working on multi-reference couple cluster theory with Jürgen Gauss. And then he joined USC, which he did a lot of work with Anna Krylov, one of the Q-Chem board members there. So that was really cool and exciting. And then in 2015, he founded his own research group. He started his own independent research career at the University of Munich before moving to KU Leuven in 2020. So we're really excited to have him here, and I look forward to hearing more about his work. So I guess we'll go ahead, and it's 10 o'clock, so it's webinar starting time. So I guess we'll go ahead and hand the reins over, and you can go ahead and start.
Yeah, thank you very much for the introduction. And I believe my screen is visible and you all hear me well. So I should start by thanking Q-Chem for this opportunity. I appreciate it very much to talk a little bit about non-Hermitian quantum chemistry tonight, or well, depending on where you are, it's not tonight, but this day is just starting, but here it's nearing the end. I believe that non-Hermitian quantum chemistry is really a unique feature of Q-Chem, and so I'm glad to have this opportunity to explain a bit more about it. It will be centered on my own work, but I'll try to weave in some comments about how it developed and who contributed what. And well, the basic idea of the non-Hermitian quantum chemistry is already visible on the title slide. It's complex valued energies. And if you look at any textbook of quantum mechanics, one thing that's always highlighted is the Hamiltonian is a Hermitian operator, and the energy is thus real. So today I want to make a case that there is some value in dropping that requirement, and that you can gain meaningful insights by using complex energies. I should say that the idea itself is very old, from 1928, so just a little younger than the Schrödinger equation itself. But in chemistry, quantum chemistry, the description of the electrons in molecules, it has really always been a topic in the niche. It's slowly changing now, but there are other areas, nuclear physics, optics, where it's really mainstream. So what I want to convey is that complex energies are maybe a little exotic, but certainly not useless, but rather can be quite helpful. So what do we use them for? Well, the fundamental idea what we want to use them for is electron loss. So in those states which are prone to electron loss are called electronic resonances. At the microscopic level, one can distinguish three types of such unstable states. So there are states which cannot bind an electron, but if you hit it with an additional electron, that doesn't mean it's just scattered off. It can linger around and so form, for example, what is called a temporary anion, if the electron affinity of that blob, which could be a molecule, is 0. Then there is a second type where you have an external perturbation, which is so strong that previously bound energy levels can lose an electron, and a bound state is turned into a resonance. And as a third type, there are states which are relevant to core spectroscopies, where you have vacancies deep down in low-lying shells, 1s of carbon or so, and those can relaxed by one electron filling that hole and another one leaving the molecule. So where is this relevant? I'm talking about electrons which leave or enter systems, so you need a lot of energy in order to have these free unbound electrons. So extreme environments come to mind as area where this could be relevant. So things like plasma, combustion chemistry, all sorts of ionizing radiation, strong laser fields. That's where it started. And of course, these environments are also relevant to more ambient conditions, because you can have ionizing radiation also interacting with biological complex matter, for example. You can have combustion of large molecules. So this is really maybe entering from the side of physics, but it's certainly relevant to chemistry as well. And a point I want to add here is, even if you say, I don't care about extreme environments, I'm not interested in these states which are prone to electron loss, you sometimes cannot really avoid dealing with them. So only if you, also if you are interested only in ground state chemistry, these states are sometimes relevant. So I just put two examples here. Let's say you want to calculate the absolute electronegativity of something. You will have to evaluate electron affinities. And evaluating electron affinities is easy if an anion is bound. So if the anion is lower than a particular molecule, you just subtract the two energies and you have your affinity, there you are. But what do you do if the electron affinity, if there is no anion below the neutral state? So this would be exactly this situation. The species X cannot bind an additional electron. You could just say the electron affinity is 0, but that's a bit simplistic, because you can have structure in the continuum. So at a particular energy, you could have an increase in the density of states, the so-called resonance, that's where the name comes from, which represents exactly this process, so a temporary anion. And it all started by looking at the electron negativity of that innocent neutral species X. And as a second example, say you want to calculate the polarizability of something. This is a well-known textbook formula, meaning that you can decompose the polarizability into a sum over states with all the excited states n contributing to it, weighted by the energetic distance to the state I. But what is all the states? Of course, it's not only the discrete bound states, but also the continuum. So if, depending on the system, the neglect of this continuum contribution in the sum can really lead to large errors, and you have to do something in order to get polarizabilities right. So with that as a motivation, let's look at in a little more detail at why these states are difficult to describe and why we want to use non-Hermitian methods for it. A good starting point is maybe to start with the standard theory, so Hermitian quantum mechanics. And a requirement that you always have there for bound states is that their wave function goes to 0 at infinity. That's so obvious that it's often not talked about, but because it's just a realization of the fact that the electron doesn't go away. Of course, the wave function goes to 0. It's not a problem if you have all the electrons bound. It leads to these beautiful discrete spectra, you can say lowest, first excited, and so forth state. But it's not a good approach if you have unbound electrons, because such a wave function like this one, which is still centered in this molecular region but has a tail that leaks out, is obviously not compatible with the wave function going to 0 at infinity, because it does not. It's coupled to this continuum background, and that's exactly what you see in the energetic spectrum. Not discrete, but you have just a continuum with a particular energy where the energy is in resonance with this particular state. So what can be done is, among other approaches, you can drop this requirement that the wave function goes to 0 at infinity. You can put other conditions. In the simplest case, we could say that the wave function behaves like a plane wave at infinity. And if you put that, there is no guarantee that the energy is real valued anymore. So this is where the complex energy comes from the changed boundary condition. And while that leads to the advantage that the resonances are now separated from this continuum background, which was in gray here, there is still a problem that this doesn't go to zero at infinity, right? I mean, we explicitly put the condition that it behaves like a plane wave. The problem with that is a bit, we would like to represent it in the context of quantum chemistry, at least, in a finite Gaussian basis set. So it would be very nice if this tail is somehow regularized. And in order to do this regularization, to ensure L-square integrability, different techniques have been proposed: complex scaling, complex basis functions, and absorbing potentials. They all result in a complex energy, but as I will show in the following, the theory that underlies them is quite different. And this is maybe a bit different in this webinar today compared to a talk at a conference. I will try to go into a little more detail about the theory of these methods and show how they come about, how they are related, and then in the end all result in this complex energy. So complex scaling is the oldest and most rigorous of these approaches. And what's always important is the reason why we do it is the divergent behavior of the wave function. So the fact that we have a wave function that does not go to zero at infinity. And what has been shown in a series of papers by these mathematicians is that you can regularize the wave function in a controlled way by doing an analytic continuation of the Hamiltonian to the complex plane. So you allow complex valued arguments here. And the fact that this is regularized is very easy to see. That's really just the back of the envelope calculation. You just replace x by x to the I theta, and then you see if you have that range for theta, this will go to zero at infinity, and in that sense, it's then can be represented in a finite basis set. There's of course a lot more math behind that. And an important detail that I want to point out is that this can be recast as a similarity transformation of the Hamiltonian with this transformation operator S, which has this structure. But this is a very special similarity transformation. It's namely unbounded. And that means that under this similarity transformation, the space on which the operator operates changes itself. And so this is only possible in Hilbert spaces which are not finite dimensional. And this is probably also the reason why sometimes people think this is black magic, because our thinking is very much adapted to finite space objects, and the intuition is often misled if you deal with Hilbert spaces which are of infinite dimension. But remember, we're looking at the processes in the continuum, so by definition, the dimension is infinite. So an unbounded similarity transformation means that many things that one knows about similarity transformations or believes to know are not true anymore. Most important, the spectrum of the Hamiltonian changes. So this is what I represented in these cartoons. In the standard case with no complex scaling, you have an Hamiltonian which has a purely real valued spectrum. Some states are discrete, that's what the axes represent, and then you have a continuum part, that's this wavy line. If you do complex scaling, the bound part of the spectrum does not change, but the continuum part does. It's rotated into the fourth quadrant here by an angle which is dictated by the scaling angle. And then in addition, you get complex valued discrete states, and those can be interpreted as resonances. So this is the basic theory, but as you see from the year here, that's not a particularly recent insight. And so you may ask what has happened in the meantime. Why do people not do it all the time? Well, one reason is this beautiful theory is only applicable if you have an exact representation of the wave function, which in our context means if you have a full basis set, because then you don't have a dependency on the scaling angle. As long as it's in that range, it's fine. With a finite basis set, you do have a dependence on the scaling angle, so you need to minimize this derivative, which of course creates a computational overhead. And as we will see in the following slides, the other methods have a similar problem. So that is one of the reasons that these methods are computationally a lot more expensive than those methods for bound states, and the reason why it's a bit out of the mainstream. Now, I should say that this particular approach, so complex scaling of the Hamiltonian, is implemented in Q-Chem for Hartree-Fock, couple cluster singles, doubles, also perturbative triples, and EOM-CCSD, thanks to mostly Ksenia Bravaya, also Dmitry Zuyev, who were members of Anna Krylov's group. And this is really the first paper almost 9 years ago that dealt with non-Hermitian methods in Q-Chem. Now, I said that this dependence on the scaling angle is one problem why these methods are a bit exotic, but there is a more severe problem, and that is complex scaling of the Hamiltonian is not compatible with the Born-Oppenheimer approximation, so it doesn't work for molecules. And to understand that in a qualitative way, I put here the Born-Oppenheimer Hamiltonian, and if you look at this, you see that there are two ways to introduce complex scaling here. You could say I scale everything, so the nuclei, the nuclear positions, and the electronic positions, and that would mean that the nuclei also end up in the complex plane, which is unphysical, because the nuclei in the end we want to treat classically, and in classical mechanics there is no room for complex valued coordinates. So what people usually do is the other alternative, or what people pursued. We scale only the electronic coordinates, and if you do it in a straightforward way, it doesn't work, because the nuclear electron attraction, which is this term, will not be dilation analytic. So the analytic continuation of the Hamiltonian is destroyed, and in physical terms, it means that this cusp condition that you get from this is unphysical. It doesn't correspond to the single cusp point that you have in the unscaled Hamiltonian. What can you do? Well, different things can be done, but I think it's fair to say that there is one particular way to deal with this problem that is really has evolved to the standard solution. At least that's my personal opinion, and that's a bit based on the observation that it's not really needed to scale all of the coordinate space. You can do something which is called exterior scaling, where you only scale, let's say, outer parts of the Hamiltonian, of the coordinates in the Hamiltonian, because it's always only about the asymptotic behavior. And this can be still recast in this form of an unbounded similarity transform. The difference is now just that this S operator has a more complicated form. If you try to do to put this into quantum chemistry, so to combine it with Gaussian functions, it's still not a very easy thing, because all these techniques for integral evaluation don't apply anymore, and that's probably the reason why nobody has done it. The other reason is that there is a more elegant way to realize this idea in the context of Gaussian basis sets, and that is the method of complex basis functions. So that relies on the observation that it doesn't matter if you scale the Hamiltonian or if you scale the basis in which it is represented, right? I mean, if you compare the left and the right expression here, it's just a coordinate transform. And while this delivers the same expectation value, so the same energy, this is a lot easier to realize in the context of Gaussian functions, because scaling the function, scaling the coordinates of the wave functions is asymptotically equivalent to scaling exponents of Gaussian functions. And then that is then where we are at this method of complex basis functions. And if you don't scale everything, so scale only particular functions in your basis set, you can basically create all sorts of operators S in this expression here. So all sorts of scaling contours in the coordinate space. An additional benefit is that the stationarity condition is usually much better fulfilled for complex basis functions than for this complex scaling of the Hamiltonian. So the results are of better quality. I think that's fair to say. But still, you need to determine this minimum of the energy derivative with respect to the scaling angle, so you still have a computational overhead. But the great advantage is, of course, it's compatible with the Born-Oppenheimer approximation, and in that way applicable to molecules. And what's really important to realize here, this is not an approximation to complex scaling of the Hamiltonian, it's an alternative of the same quality, because whatever similarity transform you do, they will all deliver the same result as long as the asymptotic behavior of the wave function is regularized. This is implemented in Q-Chem for a lot of methods now, and I don't want to talk about all of this. The one thing that really should be highlighted here is this paper by Alec White, who was a joint grad student of Martin Gordon and Bill McCurdy. And he really put this into the libQINs module of Q-Chem, that the integrals over these complex scale functions can be evaluated. So whatever came after that is really only possible because of what he pulled off. With that, I would come to the alternative, which is a lot more approximate, but in some sense also easier. That's the method of absorbing potentials. And again, we start from the observation that the resonance wave function diverges, so we need some regularization. And what was observed in the 80s is that when you put an imaginary potential to the Hamiltonian, this just achieves this particular fact. These potentials were in use earlier in order to prevent reflections in time-dependent calculations at the edge of grids, but it was more or less discovered by accident that you can also use them in stationary calculations on these resonance states. Now, what is W, of course, you ask? What is this potential? Well, it has been worked out in this paper that there are only mild conditions on this potential, and the one that is usually used is just such a shifted quadratic potential. So it's like a parabola that you put in the outer region, and it cuts off this diverging tail of the wave function. There is a relation to complex scaling, which is also available in this paper. Basically, it relies on the observation that when you put here just kinetic energy, so just a kinetic energy, a free particle plus a cap, it's something like a harmonic oscillator in a complex rotated coordinate space, and from that idea you can develop a connection. Now, for quantum chemistry, the unfortunate reality is that only if the wave function is represented exactly, the results are independent of this strength parameter eta and the potential W. Otherwise, you do have a dependence. So you have again a condition which you need to fulfill in order to find the best eta and W. And in that way, computational overhead arises. I should add that there is a correction via perturbation theory possible, but the details on that are available in the papers. This is also implemented for a lot of methods in Q-Chem, and the original papers are those two. So this is from my postdoc work with Anna, which is also now 8 years ago. And at that time, we started with Hartree-Fock and then CCSD and EOM-CCSD. I should also add here a particular advantage of this CAP method over CBFs is that you don't have to have this potential active in the whole calculation. So you could say in an EOM-CCSD calculation, I do Hartree-Fock and CCSD without the potential and only switch it on in the EOM step. And in that way, you can again save computational cost. That's not possible in the CBF method because, of course, when the basis set is complex, it's always complex. So that's a bit the theoretical background. And I would like to summarize it before I look at applications of these methods. So the basic idea is that we use these different techniques, so complex scaling, CBFs, complex basis functions, and absorbing potentials, which all deliver complex energies, and combine it with multi-state methods, mostly for the treatment of molecular electronic structure. And what has been developed as tools here is a bit summarized here. There could be other things that I missed, but I think this is representative. What I want to focus on in the remainder of the talk are actually these three ideas or three topics, which are highlighted here in the red boxes. So a bit about gradient theory and nuclear motion, then core holes and Auger decay, and then in the end I'll talk about this distortion of potentials by external perturbations. But before I do that, a very quick first look at the usage of these methods in real applications. So this is actually from the first application paper that we, I mean by we I mean in this case Anna Krylov and me, published about these methods in Q-Chem. So one way you can see these anionic resonances in experiments is if you do photodetachment. And in this case, we looked at detachment from copper fluoride. So copper fluoride forms a bound anion, and the dominating process is just the detachment of an electron. So this is this. Just go from the bound anion into the continuum. But if you hit it with the right energy and you hit the sweet spot, you can form this resonant anion first, which then releases the electron in the second step. And then the second channel is subject to different conditions, different angular distributions, and that's the way you can discern it in an experiment. What they recorded here in St. Louis, so the experiment was done by Richard Mapps at Washington University in St. Louis. What they recorded here is the orientation of the photoelectrons that come out of this experiment. That's what this beta parameter measures. What you see here is that at two particular energies, 1.7 and 1.9, the orientation really changes in all the vibrational channels, and that's exactly the signature of the second process. So that is what one can calculate, and that's what we did here. And yeah, well, the numbers speak for themselves. What I would like to highlight is that the deviation between theory and experiment is the same or of a similar magnitude for the bound state, so the one that we start in the experiment, and the two resonances, so which are responsible for the spike, meaning that the method with the cap added, this is your MCCSD here, is of the same quality as the real valued method for bound state. So this was for me an incentive to really work on this further and see what else could be explored with it. And one thing that can be explored with it is this process called dissociative electron detachment. So this is something that can happen to particular molecules when you add low energy electrons, that they just dissociate. So somebody has said it's a bit like adding a mouse to an elephant. You have a big elephant and a small mouse, you add it, the elephant will explode. And that's of course very special, because you don't need to provide as much energy with this electron as you would have to provide if you try to do this with heat. Here is what happens. So you would not have the reaction on the ground state potential energy surface, but rather on the anionic surface. And as you see, the red bar, the red arrow representing the energy of the electron would be able to be smaller than the dissociation energy of the molecule. Where does that happen? A prototypical example are unsaturated halogen compounds. So vinyl chloride, what I put here, is one of the easiest systems where you can observe that. And what makes it interesting for all sorts of applications is that you really have to hit this sweet spot. If you hit it with the wrong energy, let's say here, or here, I should say, or here, well, there is no potential curve. So the reaction only happens if you hit it with the right energy. And so it's much more selective than a heat-driven reaction. What do you need in order to model this theoretically? Well, first of all, in this region, we have the resonance character. The electron affinity in trivial sense is 0 because the anion is unbound. This is a resonance state with a complex energy until here. And the second point is, of course, that this is simplistic. There are 3 n-6 dimensions, which for this vinyl chloride molecule is already 12. And if you want to describe that, you really need to have analytic gradients. You cannot do it pointwise in terms of single point energy calculations. So we set out to develop analytic gradients, but before we talk about that, a few conceptual thoughts about nuclear motion on these resonant energy, resonant potential surfaces. For bound states, it's easy. The energy is real. The derivative of the energy gives you the force. So and the nuclei, the molecule will move to the minimum on the potential surface. There isn't much more to say. For a resonance, it's not so obvious. You have a complex valued surface, and well, I think it suggests itself, even though it's not obvious, that the real part is the force and the imaginary part is not the force, but just the change of this decay width on the surface. For more, I mean, that was of course super hand waving. For a more rigorous discussion, I refer to this paper, but I want to point out another thing here, because you can always say this is in the continuum, this surface. So there are infinitely many other surfaces around. So how do you justify the Born-Oppenheimer approximation? And the point is, you cannot justify the usual Born-Oppenheimer approximation. You really have to put more thought, and you actually get additional terms in the potential that govern the motion of the nuclei. But what has also been shown in this paper is that they are only that they can be neglected if you want to get a first insight, and that they are related to nuclear quantum effects. So in some sense, while there is more, you have to think about this a little more carefully for resonances, but it's fine to do an approximation where you just say, I take the gradient of the real part and say that is my force. And of course, we want to evaluate the force analytically, because if we do that, it's not more expensive than the energy. Otherwise, it would become quickly very infeasible. And the analytic gradient is now implemented for CAD methods, Hartree-Fock CCSD, EOM CCSD. I put a formula here to convey the structure of this gradient expression. The black parts are density matrices, and here we always take either the real part or in some additional terms the complex, the imaginary part. But for the CAP method, because we only add a potential to the Hamiltonian, the other pieces of the Hamiltonian, so the integrals, which we have to differentiate, stay real valued, so there is no additional implementation work needed. You can just take a straight derivative of the integrals as in the real valued case. You just have to combine it with different densities. And I'm very grateful here to my first PhD student, Zsuzsanna Bender, who pulled this off and who made these gradients available in the Q-Chem code. So back to our application, dissociative attachment. What we finally found is that gradients are nice, but in order to describe this really sufficiently, you have to study it in real time. So you have to go to ab initio molecular dynamics, and this can be done in a straightforward way by just feeding the AIMD code complex valued surfaces. The force is still the derivative of the real part. And in that way, we see, let's say for this vinyl chloride, the evolution on this surface. But what is more interesting and what is new for resonances is that we can also look at the evolution of the imaginary part in time. So this is what the red curve symbolizes here. And what we see is that after a very short time, so only 7 or 8 femtoseconds, it's bound already. So it reaches this point for vinyl chloride super quickly. And only after that, all the dissociation takes place. But in order to know how efficient the dissociation is, so the cross-section for the dissociative attachment, these first 8 seconds or 8 femtoseconds are of course crucial. And what we came up with here, or by we, I should actually say it was mostly my postdoc, Jerry Giamfi, who came up with it, is we invented something called the lost fraction. So this is the share of temporary anions which are initially formed and then lost at by a particular time step. And so this means the rest remaining to 1 survives. In this particular case, we have about 85% are lost. So for every 100 identical identical molecules where an electron is added, 85 lose the electron before anything happens, so before the molecule dissociates. And here we have, of course, a quantity with this lost fraction, which can be used as a proxy for the dissociative attachment cross-section. So this is what we did. We looked at particular molecules, of course, not just using a single trajectory, but doing statistics. So we ran here 200 trajectories for a couple of molecules each. Only Hartree-Fock theory. I mean, couple cluster would be a bit too expensive for molecular dynamics. And what comes out is shown here. So we did these isomers of the dichloroethylene, and then also the isomer with 3, well, it's not an isomer, the molecule with 3 chlorine atoms. And what we see is that the fraction of the fraction of molecules which lose the electron is really nicely in agreement with the experimentally measured cross-section. So that to this side, you lose more electrons, so more order detachment. To the other side, to the right, there's more dissociation, so more survives. And so I think this is really only the first application of this method. It's accepted in JPC letters, should come out every day now, and I look forward to many more applications of this capability of the code. With that, I want to switch gears a bit and talk about Auger decay. That's also a process involving, or that can be described with complex valued energies, but other than that, it doesn't have anything to do with temporary anions. It's really a different type of state. And type of state we're dealing with here are states with a core hole. So you start with a usual molecule, whatever you like, and then you can create a vacancy in a core level by, for example, X-rays. And these states can then relax using Auger decay. And what is interesting here is that they can decay into different channels. So which electron fills the core hole? That's the question. And experimentally, you would see that in an Auger electron spectrum, because these final configurations have different energies. But theoretically, it's not so obvious how to get the partial decay width. So to say, to what contribution or what share of the initially created core holes decays into that state or the third one. And that required some thought how to describe that with complex valued energies. But my PhD student Florian developed a method last year to get that out of the calculations. And this is also now published in these two papers. So I'm giving just a quick overview here. I should say there is another webinar, I think it's number 63, where he talks about this in a lot more detail. Well, the first thing to realize is in the non-Hermitian description, the outgoing electron here really never goes actually away. It just goes into a virtual orbital where it's absorbed. So we have a description where all the relevant states have the same number of electrons. And what we found is that when we look at the imaginary energy of a CCSD calculation, so the decay width, and decompose it in terms of individual amplitudes, it's really 99% due to these configurations which describe the Auger decay, so the ones where the core hole is filled. And that is a method, or that can be developed into a method to describe partial widths, because you can exclude these configurations from your CCSD calculation, either in the energy, so you just do it in the calculation in the standard way, determine your wave function, and then decompose the energy in the end, or you already exclude it during the determination of the wave function from the excitation manifold. And the second approach, which is in the second paper here, that's of course a bit of a generalization of the core valence separation, because if you exclude all of these determinants, you have just precisely that, the core valence separation. Everything is quenched, so you don't have any Auger decay and recover a bound state. What comes out? This is a table with some numbers for neon. So we have here in blue numbers which correspond to excluding excitations from the energy. So that would be the first method here. And then the second one are the numbers in red. And we did this with complex scaled CCSD as well as EUM CCSD. And we compare it to a totally different method, the so-called Feschbach-Fano approach, where you construct the wave function of the Auger electron explicitly. Well, as you see from these numbers for neon, this is a good example because you have just 5 main channels and they are experimental numbers for the partial widths. What you see is that the exclusion of the excitations from the wave function works nicely for both CCSD and EUM CCSD. So this is always reliable. The blue method, decomposing the energy, is only applicable to CCSD. EUM is unreliable, and that is something that is still under investigation. But we also learned something about the Fano method, namely that it matters how you model the Auger electron. A Coulomb wave gives you a much better result than using a plane wave. With a plane wave, some of the partial widths are really distorted. This was for an atom, right? Just neon complex scaling of the Hamiltonian. When you want to do molecules, you have to be careful because you have to pick the complex basis functions. And this is something that really required a lot of thought for this Auger decay. Because what we found is that the usual wisdom applicable to other resonances, that you use diffuse functions that you scale, is not true here. And I just want to give a brief indication of what's the problem here by looking at the dependence of this exponent, or by looking at the dependence of the imaginary energy, so the decay width, on this exponent. And as you see, the decay width is here, the blue one. There is really a sweet spot. If you put the complex scaled exponent in the wrong range, you don't see anything. And you really have to optimize these so that the energy becomes stationary with respect to the scaling angle, and then you get good decay widths out of it. And we found that this particular basis set, so a Dunning basis set of triple zeta quality, where the triple zeta part for the S and P functions is replaced by the part from the 5 zeta functions, delivers very good results with just 2 shells, SP and D, each complex scaled. Here is an application case, benzene. This is pretty complex because we have 6 initial states of the core ionized benzene. There are 6 carbons, each with a core hole where you can remove the electron. Then you have at the same time more than 1,000 final states in principle into which they can decay. So there's a lot of work necessary. And I'm very glad that we have a spectrum ready, and we actually have 2 ready because this is a joint project with the group of Anna Krylov and her PhD student Nayantara. So they prepared the orange curve, which is based on this Feshbach-Fano method, where you describe the Auger electron that goes out explicitly. And my PhD student, Antoine Ferrino Perez, did the blue curve, which is based on our theory of complex basis functions. And what I really like here is 2 completely different descriptions of the continuum deliver 2 spectra which are in quite good agreement. And at the same time, there is also not a bad agreement with the experimental spectrum. So this is really promising, I think, and I hope that in the next talk I give, I can replace in preparation by submit it or so. Now, I do have a third part on strong field ionization, but given the time, I believe I skip that and come right to the conclusions. I want to reiterate that non-Hermitian quantum chemistry, complex energies, is really a signature capability of Q-Chem. There's no other major program package that offers that. It's applicable to very different physical phenomena: temporary anions with electron affinity 0, core holes, Auger decay, and then this field ionization, which I skipped. And a nice feature from my perspective is that all the techniques that have been developed for bound states, concepts like potential surfaces, orbitals, molecular properties, transition moments, and so forth, they are all applicable. Sometimes there's, of course, it's needed to have changes, to consider changes, but the basic ideas are applicable. And by now we have really many methods available in Q-Chem, and I want to highlight in particular these recent additions, so ab initio molecular dynamics and partial decay rates for Auger decay. That's not yet checked in, but I hope that changes soon. There also are RI approximations and quantum embedding, about which I didn't talk today, but they are already available in the code. And before I stop, I have an acknowledgement slide. I want to first thank all the people who have contributed to this capabilities that Q-Chem now has. I think it's fair to say that without Anna Krylov, there would be no non-Hermitian quantum mechanics in Q-Chem, because she really started it with Xenia, at that time a postdoc of her, and then Dima Zuyev, who was a PhD student, and then I think I was the 3rd person to join that gang. On the other hand, completely independent of us at USC, there was Alec White, in Berkeley with Martin Gordon and Bill McCurdy, who worked on the complex basis function code, while we did mostly CAPS and CS before. On the other hand, on the other side of the slide, we have, so to say, the second generation. I want to highlight in particular Jana Bender, who was my first PhD student and put gradients for complex for CAPS into Q-Chem. Andreas Treuf should also be mentioned. His group is responsible for the development of all the ADC, complex valued ADC methods in Q-Chem, which are in many ways closely related to coupled cluster. I also want to thank all the members of my group, which are listed here. And I stop by asking you, if you're interested to join my group, you could check out this link where we have an open PhD position together with the University of Melbourne and Lars Görig there. So thank you very much for your attention.
Thank you so much for the talk. That was awesome. I am going to now open the floor for questions. It looks like we've already got a couple in the chat, and one of the attendees also. You can either ask a question in sort of the little questions box down there, or you can raise your hand using the little hand-shaped icon. So it looks like Narayan is the first person. So I'll go ahead and unmute you, and you can go ahead and ask your question. Can you, are you here? All right, here. Okay, can you try now? Okay. If you are trying to speak, we cannot hear you. So I guess we'll go ahead and move on to the next question. But if you want to drop the question in the chat or on the forum, then we'll try and get around to answering that. So the next person, there looks like there's a question from Abhishek. So is there any chance of getting non-physical stabilization points using the CBF method? Is the question that he's asked. So
yes, there is certainly a chance to get these. So there are cases when you get two, well, I put this derivative, right? That I should go back to that slide. I put for CS and CBF, you have to minimize this derivative, but I didn't really show how the dependence of E on theta looks like. And what is unfortunately true is that there are cases where you have two minima. And I think it's fair to say that in most cases, it's obvious which one is the right one, but sometimes it's not. And of course, it's not a good, a feature of the method that exists. Because you specifically asked about the CBF method, I would like to add that in CBF, as in CS, you have this restriction on the scaling angle. So it goes only from 0 to pi over 4. And that's a much better situation than CAPS, because the eta, the strength parameter, is unbounded. So in principle, it can be arbitrarily high. And you also have this box size in W. So yeah, short answer is there are these unphysical stabilization points, but they are, in my opinion, a much smaller problem with CBF than with CAP.
okay, awesome. Thank you. And I'm looking to see if anyone else has raised their hand. Oh, okay, there's a couple more questions in the questions box. So the next one is from Vale Kofer Shabika, and he is asking about for the lifetimes of the temporary anions, you mentioned approximating the dynamics on a manifold of complex valued potentials with a single real valued potential. Could you please comment a bit more on the assumptions you're making and where they might break down?
So the potential on which the anion evolves is still complex valued. It's just that the force is only the so these potential surfaces that we evaluate here, or these simulations that I'm showing here, they are all run on complex valued surfaces. I think the point is the force is only the derivative of the real part. And so I guess it's about what is the, under which circumstances would that assumption break down? And I think there are two situations I could imagine where it breaks down. First is very broad resonances. So prototypical example would be H2 with an additional electron, so H2 minus. That is super broad. And there are actually papers from long ago. H2 minus is very small, which show that this so-called local complex potential approximation is very bad for H2 minus. So broad resonances is one case where it fails. And the other case would be very close to the threshold, because well, the way to understand that is that the resonance has a width, right? But width should never leak into the bound part. So if you approach this crossing point, this local description can obviously not be the whole truth. And that is where it breaks down as well. But I should add here that there is a discontinuity in our calculations anyhow, and that's because it's also getting difficult to determine the optimal cap parameters at this crossing point. So yeah, these are the 2 points, but I think the first one, broad resonances, is a lot more relevant to applications of our method.
Okay, awesome. Thank you so much. I was wondering about that discontinuity a little bit as well. So what makes it, if you don't mind me putting my own question here, what makes it hard to determine those at the crossover point?
Well, in some sense, I could say it just, at the technical level, it's just not possible to determine a minimum here, in the sense that there would be no minimum. And yeah, well, what's the reason? Well, the reason is that the basis set is just not capable of capturing such small widths, because this potential is not only absorbing the electron, it's also a giant perturbation. And so if you add that to the Hamiltonian, you cannot, well, you can correct the perturbation, but you cannot really avoid it. And so yeah, that's basically the reason.
Okay, that's interesting. Cool. Okay, sorry, we've got 2 more questions, so I'll try to get to all of these. So Yisang Wang has asked how to decide the gamma value, so the imaginary part of the energy.
Well, we don't need to decide it, it comes out, right? That's the result of our calculation. We just well, I didn't put any technical details on the way these calculations are carried out, because whenever I prepare such a slide, it just looks like the standard method. That's a bit the deceiving fact about these methods. They look on paper like the real valued methods. It's just that the complex valued energy comes out. And so in that sense, that's, I think, the biggest plus of all these techniques, whether it's the CBF or CAP or CS. You don't have to make any assumption of about gamma, it just comes out.
Okay, that makes sense. Thanks. And then Julia Aragon has asked, she would like to ask if non-Hermitian methods should be considered in the non-covalent interactions that are strongly related with the polarizability properties.
I guess that refers a bit to what I said in the beginning about polarizability. Yeah, well, you need polarizabilities for an accurate description of non-covalent interaction. That's right. But this is, what I put here is really at the moment just a thought. So I haven't really done much computations on that. In that sense, I don't have any numbers that could that could allow me to give a substantial answer. But if I speculate about this, the question is how relevant is in this sum the continuum contribution? If it's small, there's no problem. You don't need any non-Hermitian method. And usually it is small. I mean, it's not that all the polarizabilities that come out of the standard methods are wrong. My point is just there are cases when this continuum contribution is large. And when would it be large? Well, anions are a typical case. Bound anions, let's say in this cartoon, this particular state. If you look at the polarizability of this particular state, there wouldn't be any contribution from a discrete state. It would be pure continuum. So I think your original question comes back to, or I would translate that to the question, how relevant are non-covalent interactions for these, let's say, anionic states or other states where the continuum contribution to the polarizability is large? That I think one would have to consider.
Cool. Cool question, cool answer. So we actually have one more follow-up question, I think, to one of the earlier questions asked by Balanarayan Pananghat. So he says, as a follow-up, does the imaginary part of the force have a physical meaning of tunneling?
I mean, the short answer is I do not know, but the question would be through which, I mean, tunneling, I would ask through which potential barrier. And of course, the imaginary, I mean, was the question about the derivative of the imaginary part or the imaginary part itself?
I think it's about the imaginary part itself. Yeah. Just
well, in that
based
sense,
on the phrasing.
I think one could say it's always characterizing a tunneling process, because I mean here it's most obvious that the electron leaves such a molecule because it can tunnel through that potential, through that distorted potential. And you can draw similar pictures for these temporary anions where the barrier would be due to the angular momentum. So yes, it's due to tunneling. And well, I'm careful now to say it's always due to tunneling, but I cannot think of a case where it's not related to tunneling. So probably it's true. It's always because of a tunneling process.
He said the imaginary part of the force, not.
Okay, yeah, so then.
Sorry.
Well,
sorry, I just saw the imaginary part and fixated on that. So.
Yeah, now I answered it about the imaginary part of the energy.
I'm sorry.
So in that
I'm
sense,
sorry. Yeah. That's my
fault. Mean, the force is just, or the derivative of that would just be, yeah, how that changes as a function of the coordinates. So in the sense, how does the shape of this potential adjusts if you rearrange the nuclei somehow? I mean, that's the meaning of the imaginary part of the force. And yeah, so in that sense, how, yeah, in what direction, I mean, what arrangement of the nuclei would facilitate the decay and what would make it harder?
Yeah, that makes sense. Thanks so much. And then a couple of people have also just said, you know, thank you for the presentation. And it was a good and fun and informative talk. And it's really cool to see all of this really exciting work.
Well, yeah, I appreciate it.
Yeah, we really appreciate having you. If anyone else has any additional questions, we're just about at the 1 hour mark now, but please feel free to ask about, you know, any lingering questions you may have. You can ask them on the forum. We've got a webinar post that, you know, the topic is there. So any other questions you can ask there. And yeah, just thank you, Professor Jagau, for all of, it's a really great and informative talk. And I think we all learned a lot. So
yeah, well,
cool
thanks
work.
for having me.